All right, my friends, welcome back to Uncertainty and Probability Theory, the Logic of Science. I'm William Briggs. We're on episode 38, Truly Random and Information Complexity. We're going to be talking about information theory and randomness and how they tie together and what they mean by randomness and what I mean by randomness, and they're not quite the same. We're not going to exhaust the subject of randomness nor information theory. We're going to come back to it later when we discuss entropy and information content of probability distributions and all that kind of a thing. Right now we're going to think about something difficult. Let's do a little review first of how we think about how we think. Remember, we said that the most important information that we have is got to us by intuition, by induction, I should say, by induction of various sorts. Remember, there were various sorts of induction. There was induction intellection. Induction intellection is where we take the data from our senses. For instance, how do we know there's an infinite number of numbers, we might say? Well, we take information like 1, 2, 3, 4, and we look at that and we say, based on this, well, I don't see how this can exhaust itself. So we make a leap to infinity. We make a leap to infinity. So we take limited sense data, finite sense data, and we make a leap to infinity, to a universal. All universals are infinite in a sense. They're completely in their own realm. You know, this is almost like a Platonic realm kind of a thing, although I happen to be more of an Aristotelian about forms and essences and so forth. And we're going to come to that when we talk about causality. This is finally leading us to causality. But we do have a way where we take finite sense data and we jump to the infinite. Let's just stick with math. We've done this axiom before. This is one of Peano's axioms for arithmetic. We note that for any numbers x and y, just numbers, integer numbers, counting numbers, we note that if x equals y, that y equals x. So we can do this sort of switching around kind of a thing. All right, this seems absolutely true. And now we're going to say that we could do it for 1. Well, it works for 1. If x equals 1 and y equals 1, then x equals y and y equals x. Okay, what about x equals 2, y equals 2? Well, it seems to work for that, and it seems to work for this. Now I'm going to say for all numbers that this is true. Now, I've taken a finite amount of sense data, a finite amount of intellection, and I've jumped to an infinite number. I have in front of us an axiom. This is an axiom. It is a statement for which those who care to think about it and those who can understand it can see its truth, but for which there is no truth. In a sense, it is a minimal statement. This axiom is, in a sense, a minimal statement. It's a minimal statement about all of the numbers from 1 to infinity. All right? So in a sense, and this is the strange thing about information theory. So we're going to be looking at what they say about information theory. In a sense, because it is we don't know where it comes from. The proof we don't understand. The explanation for this we don't fully grasp. But we can see its truth. Not everybody can see its truth, but some people can see its truth. And for those people who do see its truth, well, that is to say, it's a very difficult thing to explain, but in a sense, it is minimally expressed. All axioms are minimally expressed. And this is the strange thing about information theory. They say a number is random. A number or a piece of information is random if there's no simpler explanation for it. Okay, so axioms in this sense are random because there's no simpler explanation for the truth of the axiom than just stating the axiom itself, because that follows from that there's no proof. If we had proof for the axiom. Of course, the axiom wouldn't be an axiom. It would just be a theory of some system. So we're going to talk about that in a second. So it's all going to come back to this. It's going to be coming back to Gödel's theorem and Kolmogorov and Solomonoff complexity. So let's think about this. Let's think about it now. I've given you the kind of overview to this. Now we're going to think about this in a sense. If I have this number here, just a number 9, and I want to simplify that, and I want to transmit this information. I want to transmit this information over whatever computer system that I happen to have. This computer system, of course, will have, it'll have a language, it'll have a grammar, it'll have rules, it'll have its own axioms of how it all works or whatever. So all that's part of it. Remember, when I said probability is always conditional on all the premises that you use. And I always insist that it's conditional on the grammar, it's conditional on the definitions, the rules that you're using, all the logic and everything. All of that is in every probability statement we have. But it's not written down. It's tedious to write all that stuff down for every single probability question that we ever have. It's tedious, too, in mathematics when you're proving a theorem to write down the list of all of the theorems that lead you back to the axioms. Whatever set of axioms that you're using to start off in your formal system. This is a formal system. So a computer is, of course, a formal system. It doesn't matter. It's only formal in the sense that it has these things. It has some sort of syntax, grammar, rules, axioms. All of these things that make it together, that make the thing work. Like our language, English, or whatever language you happen to be using. So if I want to transmit this 9 in this particular formal system, it doesn't seem to be any way of compressing this any smaller than 9. So the information complexity people would say number 9 is random. They usually start off with things like this. Well, let me just start with this. Keep with my 9 right here. So I want to transmit. They would say it's random. The number 9 here I wrote up as random because there's no way to simplify this. And so a lot of times you'll open the books. They'll say, well, they do it the hard way. They do the proof the hard way. They'll write a series like this, a binary series like this, and then they'll write another series, something like this. And they'll say, aha, well, we can notice the pattern in this one right here, and that's just repeat this, 01. So if we lengthen this series right here, it's easy to see that this repeat 01 is shorter in complexity than the series that I have right here, if I'm going to carry it out to n times or something like this. Repeat this n times. So this is more compact than this. Therefore, this is more random than this is. This looks more random to the eye because there does not seem to be a theory, let's just use that word, a theory or a model which is more compact than this series. In other words, I could write it out in whatever this formal system is. It doesn't make any difference, of course. You change from one language to the other. Sometimes you need to use more words, or sometimes you need to use fewer words. And when you're using certain programming languages, you need to use more or less, and it depends on the system architecture. All that's part of the formal system. We always have that. Those are always going to be our implicit or tacit premises. But I say that there is if I cannot discover a theory or model that compresses this data in a way that is shorter than the series itself, however long it's going to go, then this itself is random. But if I can find a theory or model that makes this more intelligible, and I can compress it like this, then this theorem is supposed to be random. That's the definition that they use. The shorter it is. Now, the funny thing about this, it should be sort of obvious to you. I think it's obvious. Like, for instance, they do it the hard way by showing these long series. But how many different theorems are there in the world that would generate the number 9? Well, we could have 10 minus 1. That's one particular explanation for this number 9 here. I could have had 8 plus 1. I could have had 11 minus 2. I could have, in other words, it's easy to see, I think, there is an infinite number of possible theorems that explain this number 9. Why is this number 9 here the way it is? All of those are larger in complexity than the number 9 itself, so the number 9 is said to be random. But if we're trying to do, this is leading us into models and so forth. If I want a model for this, a theory for this, this is, of course, more compact. Repeat 0, 1, however many times. 1, 0, however, look at this. You guys got to catch me on this. Repeat 1, 0, however many times it happens to exist. How many different theories are compatible with this? Well, there's still an infinite number of theories. It could be repeat n 1, 0 n times, and after that repeat. Then it moves to 0, 1, 1 or something like this. You can keep. In other words, if you go out to n times, it does that, and then all of a sudden the series changes. We don't know, we don't see it, because all we have in front of us are these digits right here. So the point of that being, any set of data that you happen to take, here's the, if I'm being mumble-mouthed, any set of data, any data is compatible with an infinite number of theories or models or explanations. All right? That's just the case. This is why the hope of finding a universal model or a universal truth generator, this is part of the proof behind it. You'll never find such a thing, because there's an infinite number of models that are compatible with any set of data that you happen to have. Absolutely any set of data that you have. But the hope is to find the one that's the most compact, and the one that you could find that's the most compact, you'll say, is random. Now, you know, you could show a series is not random. If someone gave me this series right here, this 10, 10, 10, 10, 10, I could say that's not random in an information theoretic context within this formal system right here, just by showing that I can come up with this particular theory or algorithm for it, which is shorter. Okay? I can come up with this, which is shorter. And therefore, this series cannot be said to be random, and I can prove that it's not random in the information theory sort of way. But I can never prove that a given series of numbers that are greater than the complexity of the system as a whole is random. I can prove that something is not random. I cannot prove that something is itself random. And this has to do, and I'm not going to prove all this kind of stuff because I think it's beyond what we're doing here. Maybe I'll do a separate video on this alone. But it goes back to Gödel's theorem. Gödel's theorem. Spelling doesn't count in this class. That you cannot prove some statements. In other words, you'll have a certain formal system right here. You'll have this formal system. It's all the same. All this stuff is the same. It all ties back together. And this is going to be called underdetermination eventually, that we can't find any kind of theory. So we have this formal system. And basically what I could do is I could give a well-formed string. I can just a string of 1 bit long, or however, whatever the language is. The simplest string I could feed into this system. And I can ask, is this true? Is it true or false? And the system can spit it out, and I can go to all such strings that are of that length, one word long, whatever, 1 bit long or something. I can ask whether or not it's a derivable theorem from this system. And then I can go to ones that are 2 bits long. Then I can go to ones that are 3 bits long. And I can keep asking this thing. I can keep asking this system, are these things true or not? I can keep going on like this forever. And every one that is true becomes a theorem of this formal system that I could use. So you should be thinking artificial intelligence about this point. Artificial intelligence is exactly this kind of a thing. I could feed it all this kind of the idea, and I could just go through sequentially all possible strings that are compatible or well formed with this formal system. And I can check whether or not they are true. But there will be some theorems that are true but cannot be proved true by this formal system. And namely, it's those that are more complex than the system itself. And what are more complex than the system itself? Well, I don't know of any in mathematics. I don't think anybody's proven it. So if you're looking at calculus or something, I don't think people have found statements that are true but not true inside mathematics. But it is the case that this is true. And let me put this another way. It's trivially true. It's trivially true. It's absolutely trivial true. Gödel's theorem is absolutely trivial true because the axioms themselves cannot be explained by the system. The axioms are those statements, those propositions in logic or whatever, that we take as true, that we assume is true, that we have no proof is true. That's the crucial part right there. We cannot prove they are true. They just seem to be true. By induction, intellection, we assume they are truth. They just seem true to us. There's a whole list of these axioms. Some of them are not necessarily seen so easily to be true, like in something called the axiom of choice. And that involves infinity. Remember, we've got to be very careful about infinity. I'm not going to go into the axiom of choice except to say you have a bunch of sets, each of which has certain members in it, and the idea is, can I take at least one element from every one of these sets to form a new set? Seems pretty trivially true if the number of sets are finite, but what happens when they're infinite? Can I still do that? Well, infinity is tricky, and so this axiom of choice, there is a dispute over whether or not such a thing is true. So it's not that, again, I want to stress very strongly, there's all kind of things. When we grasp an essence, when we grasp a nature of something, we're not necessarily grasping entirety or the full nature of something. I guess I had a discussion with some gentlemen the other day where we're talking about the essence of a dog. When I say dog, you have an idea in your mind about what a dog is with variations on that. But does anybody know the full essence of dog? I don't think anybody could. Because there's always seems to be something new to discover, something we know some basic minimal things about the nature or essence of a dog. So we can grasp that. But it doesn't mean just because we know some of those that we know all there is about a dog. Okay? So that's going to become important when we discuss cause and so forth. But there's just, anyway, I want to come back to this sense that it's absolutely true that we know axioms, or at least some axioms in mathematics are the simplest ones to demonstrate, and logic too. Because they make a lot of sense for those who are kind of quantitatively minded. But not everybody understands all axioms. I want to keep stressing that because it's some axioms that some statements that people have, they claim are true, turn out not to be true, or turn out to have contradictions, or turn out to be able to be derived as theorems of a simpler system and so forth, which are not axioms themselves. So because people have these facilities of intellection, of the nous and everything, it doesn't mean that everybody has them equally or people don't make mistakes. I mean, a drunk guy, for instance, might mistake, he walks into the zoo, he's drunk, he mistakes a lion cub or something for a dog. Right? So he's mistaken the essence of a dog. That doesn't mean that there's no such thing as dogs or people can't tell them apart. We're not nominalists here. Okay. Now, I don't love the information complexity idea of randomness. It's a perfectly useful concept in computing to say that if I can't, there's all kind of, I can have strings like this and there's all these compression algorithms that are out there. Lossless compression algorithms out there that try to take these series, and what they do is they just try to find patterns in these series and everything, like in images and so forth, and compress them down into a minimal state. Into a state, rather, that is not minimal, into a state which is smaller, which is to say of less complexity than the series itself, and therefore more random in the information theorists' sort of definition. Nothing in the world wrong with that. That's fantastic. All that kind of stuff's wonderful. But it doesn't necessarily capture the full definition of random, okay? Now, I've been stressing that random means unpredictable in the sense because we don't know the full cause. We don't know the full explanation for a thing. So I use this particular thing because it happens to be the millionth digit of pi. And I looked it up, but I didn't have to look it up. I have you'll see in the class notes today, the millionth digit of pi can be had by an algorithm. There's an algorithm of the nth digit of pi, that runs in finite time, as long as n is not itself infinity. We could find the nth digit of pi. All we have to do, and we don't have to know the n minus 1th digit or the n minus 2th digit or n minus 3. If we just want the nth digit of pi, that's all we're interested in. There's a nice little algorithm. There's an equation that forms the basis of this algorithm. It's very simple to look at and everything, no difficulties, and we could find this. So in a sense, if you ask me, the information theorist would say, here's pi. And I could transmit pi, the digits of pi, up to the million, and that's very random. But of course, I could compress it down into this algorithm. This algorithm is a very short equation. It's not very big at all, and just give you that. And that's a lot smaller. And this algorithm of pi, therefore, is less random than pi. But of course, pi is transcendental. Pi's digits go out to infinity. They never stop. They never repeat. No sequence inside them repeats. It just goes on and on and on. So in that sense, pi is random. But in the predictive sense, I know, using this algorithm, I know with certainty what each digit is going to be. Okay? So in the strictly predictive sense, I know what's going to happen. All right? So that algorithm is like a correlation. And it still doesn't prove causation because I still have not explained why pi is 3.14 ... all these dots. I still don't know this. I have an equation or an algorithm that gives me each of these digits, but I don't know why. I don't have the explanation why. I don't know why the Lord himself chose pi to be this particular transcendental number that goes out forever, that has a certain sequence, and that happens to have the millionth digit happens to be 9, or the trillionth digit, whatever it happens to be, or the Googlest digit, whatever it happens to be. Why did it have to be that and something else? Why can't it have been something else? I don't know. And so that is random to us. That part of the explanation is still random. The why part. And the why part is a very important part of causality. Causality has different elements, all right? That part of the pie we'll never know. I think we'll never know. We'd have all kinds of equations for it, but we don't know why it's this and not something else. When we reach that level, it's similar to the information complexity idea, but applied to a different, not the predictive sense of it, but applied to the nature of the thing itself. So the information complexity people are focused on a narrower range of things, and that's fantastic. It's great that they are, to our great benefit and all this sort of thing. But it's not complete. It doesn't tell us the why, and that basically is it. We sort of gone through this whole thing, and basically all we've done is, is just a review, really, if you like, of one of the first classes we did when we talked about, there's information argument, there's information induction, intellection. That's how we know the truth of certain axioms and essences and natures and so forth. We have induction argument, we have induction intuition, where we have these flashes of insight where we move from the finite to the infinite in an instant, which is something no computer can do. And information intellection is something no computer can do. A computer is stuck in a formal system. A computer is stuck in a formal system, and it can prove theorems about them forever, you know, in a theoretical sense. It can prove all theorems that are compatible with this and of less complexity than the system itself. That part is absolutely true. But it can't prove anything that is outside the formal system and is more complex than it, like axioms are when we start out this thing. Axioms are kind of below, or the first formal system, axioms. And then we have the formal system, the formal computing system here. And this thing may give information just like our senses give us information about the finite. And we may use all this kind of stuff to infer what's going on. We may have flashes of intuition in which we look at the output from these AI systems and so forth, and it tells us something, a new axiom. It tells us a new axiom, a new insight, perhaps by analogy and all this kind of a thing. And finally, of all those inductions, the last one is induction probability. Induction probability tells us we could do something like this, but then we can have a conditional model that gives us, you know, pretty good consonance with the data, but it doesn't guarantee that correlation doesn't become causation, because there's an infinite number of potential models that explain these kind of things. So we're way down on the list. Induction probability is the least of the types of induction that we have, the least of these kinds of knowledge. And so we have to be very careful about how we're going to eventually use models and all this kind of stuff. That's the whole point of this kind of thing. What are models really telling us? And why cannot correlation be causation? We've learned why right here. We can have perfect correlation, but we still don't have causation, not the full causation. All right, so now finally, all of this, we're finally leading up to causation. That'll be the start of our next lecture, chapter 39, episode 39. We'll start on causation. And then finally, once we have under our belt all of this stuff, and we're sure we understand, we're not going to fool ourselves by correlation, we have a firm grasp on causation, then finally we'll move to the more informal kind of modeling, or they call it a formal system, but it's much more informal than causation is. And we'll finally get to the practical day-to-day kind of statistics and probability, AI, all that kind of stuff, and why all that fits in here and what it can do. I mean, you can program a little bit of AI to generate some of the analogy and some of the argument and so forth, but you're still going to be stuck in that system. You're never going to bust out of it. But it can be used. It certainly can be used by minds to make leaps forward and so forth. So this is not an argument to say don't use models. Of course we use models. Of course we're going to use them well, and we're going to cherish our good models. And that's the whole point of this. But we're going to learn to disparage the bad ones, of which most are. And I'm going to prove that to you too. All right. Again, a lot of information. I'm going to have links to, I'm going to give a excerpt of uncertainty and so forth, and some links to some other articles. You can read more about the more difficult things of these in depth. And I'm also writing some articles on the limitations of AI, which go into like Gödel's proof and the Solomonov's proof and Kolmogorov complexity and so forth, and why these sort of show AI is just a machine. It won't come alive. You know, they're not going to develop minds like we have and so forth. As a more formal proof. But that's a separate thing from this class. Maybe I'll do a separate video on those. But I just wanted us to see where we're going, and I hope you guys are making use of these kinds of things. And you know, pass these on if you can. I know it's difficult. All the classes are numbered 1, 2, 3 and everything, and it's intimidating. Oh, am I really going to start with class 38? I try to make most of the lectures somewhat internally coherent so you don't need to. But of course, most people will not see that, and so you can help me out by showing these around. All right, that's enough. I've talked too much. Information is down below. They'll be at my sites, and that's it for this time. Thanks very much for listening.